Applications of thermal expansion of solids. Electric and telephone wires. Wires are arranged loosely between poles to prevent them from breaking in the winter when they contract. Bridges and railways. Expansion joints in bridges and railways allow the structures to expand and contract with temperature changes, preventing them from buckling or collapsing. Thermometers. The liquid in a thermometer moves up or down a tube in response to changes in temperature. Windows. Rubber spacers are used in metal-framed windows to account for thermal expansion. Electric glass bulbs. Tungsten is used as a filament in electric glass bulbs because its linear expansion coefficient is similar to glass. This allows both the glass and the tungsten to expand equally, preventing the bulb from failing. Bimetallic strip. A bimetallic strip is a device made of two different metals that are joined together, usually in the form of strip. Principle of bimetallic strip. Bimetallic strip works on the principle of thermal expansion. It is made by bonding two different metallic strips. They are steel and copper or steel and brass. The coefficient of thermal expansion of these two materials are different at the same temperature. On heating, these two metallic strips expand at different rates and create bending effect. When temperature increases, the bimetallic strip bends towards the metal having lower coefficient of thermal expansion, and when temperature decreases, it bends towards the metal having higher coefficient of thermal expansion. See the diagram, you can understand clearly. Bimetallic thermostat. A bimetallic thermostat is a device used in electrical gadgets to automatically control temperature. It works based on how different metals expand when they are heated. The construction. 1. Bimetallic strip. The main part of the thermostat is a bimetallic strip made of two different metals joined together. Commonly, one metal expands more than the other when heated. Examples of metals used are steel and copper. 2. Electrical contacts. At one end of the strip, there are electrical contacts that connect to a heating circuit. 3. Casing. The whole setup is placed in a casing that fits inside electrical appliances like irons, heaters, and ovens. Working. 1. Initial state. At normal temperature, the bimetallic strip remains straight and the electrical contacts are connected, allowing current to flow and heat the appliance. 2. Heating up. When the appliance heats up, the bimetallic strip also heats up. Since one metal expands faster than the other, the strip bends towards the metal that expands less. 3. Breaking the circuit. As it bends, the strip eventually breaks the connection between the electrical contacts, stopping the flow of electricity. This prevents further heating. 4. Cooling down. When the appliance cools down, the strip returns to its original straight shape, reconnecting the contacts and allowing the current to flow again. This process repeats, keeping the appliance at a set temperature. Thermal conductivity of solids. When a part of a metal is heated, the electrons in that part gain energy and begin to vibrate in place. These energized electrons transfer their energy to neighboring electrons, causing them to vibrate as well. This process continues, allowing heat to move through the metal without any net movement of the particles themselves. This phenomenon is called thermal conductivity. Metals are good conductors of heat due to their free electrons, while non-metals, having tightly bound electrons, do not conduct heat effectively. Definition: the ability of material to conduct heat is called thermal conductivity. Expression for thermal conductivity of a solid. Consider a rod of length x, area of cross-section A. T1 and T2 are temperatures. Here T2 greater than T1. We know that heat transfer between two bodies only happens when there is a temperature difference, so the heat will flow from T2 to T1. Now let's see what factors affect the flow of heat energy. 1. Temperature difference. The heat energy flowing depends on the temperature difference between the two ends. It doesn't matter how high or low the temperatures are, what matters is the difference. If both ends are at the same temperature, no heat will flow. But if there's a significant temperature difference, the heat flow will increase. Q is proportional to T2 minus T1. 2. Cross-sectional area. The heat flow is also proportional to the cross-sectional area of the conductor. If the area increases, more heat energy will flow. A larger cross-sectional area allows more heat to pass through. Q is proportional to A. 3. Time. The heat flow is directly proportional to the time T in seconds. Q is proportional to T. 4. Length of the conductor. The heat flow is inversely proportional to the length of the conductor. A longer conductor reduces the heat flow, while a shorter conductor increases it. For example, if we take a small rod and a long rod of the same cross-sectional area and expose both to the same temperature difference, the longer rod will have less heat flowing through it per second due to its greater length. Q is inversely proportional to 1 by x. Combining all, we get Q is proportional to AT into T2 minus T1 by x. Q is equal to KAT into T2 minus T1 by x, where K is a proportionality constant called coefficient of thermal conductivity. Definition of coefficient of thermal conductivity. It is defined as the amount of heat flowing per unit time through a unit area when the thickness is unit length and the temperature difference between phases is 1 unit. The SI unit for K is joule per second per meter per Kelvin, which is also referred to as Weber per meter per Kelvin. Thanks for watching Pathfinder6. Like, comment, share and subscribe to my channel.